Well, hello everyone. My name is Hanav Modasiya. I'm a high school researcher from Santa Clara, California, and this is my presentation, Resolving Gender Biases in LLMs at Inference Time with novel Dijkstra's based K-explorers Neural Network Traversal, or KeNNT. It's a mouthful, but uh, that is the algorithm I created. So here are just the contents of my presentation. Let's go into a brief introduction about the topic and the problem I'm going to solve. So large language models like ChatGPT, Llama, and Gemini have gained popularity among developers and the public. And these transformer-based models trained on large internet datasets often inherit stereotypes, including gender biases. So as a result, LLMs frequently associate males with technical roles and women with domestic roles. Like, for example, they link the word he with mechanic and the word she with assistant automatically without any other context, as seen in this sentence. So just about the previous solutions to resolve gender bias, they generally fall under two categories. The first category of solutions modify the training dataset and the word embeddings to reduce the bias in the outputs. However, this can distort the original dataset and oversimplify gender relationships. The second approach mitigates biases during inference time after the model has been trained by using effective prompting that the prompts basically discourage gender bias reasoning. And while these are effective in short interactions between the user and the bot, these prompts often fail in longer chats as the model may forget the original prompt. However, my solution addresses these three limitations and it avoids modifying the dataset, works during inference time, and even works for larger text, hypothetically. And before going into the actual research, let's just go over the benchmarks tools that we used. So to test the algorithm I created, we tested on WinoBias, which is a commonly used gender bias data set. You can see some samples down there. We used co-reference resolution to help our algorithm, which calculates pronoun and noun relationships in a text, as you can see on the other side. And finally, we use Dijkstra's algorithm, which is a shortest path finding algorithm in a weighted graph, which finds the shortest path greedily, which is very important, greedily, from the start node to all the other nodes. So to begin, let's talk about how we can frame the problem of gender biases in LLMs to be a graph solution problem. So to start, we frame the transformer model as an autoregressive search algorithm. Well, why? Well, because at any time, the transformer is searching for the next word that it should spit out from its vocabulary. So we can imagine the transformer as an explorer that's moving from left to right through this graph of word choices, where each layer represents like a certain index for the word, and each token, each node in the layer represents a possible token that could go in that index. So when the transformer creates a sentence or a text, it essentially creates a straight line from the left side, from the start token, the start of sequence token, to the end of sequence token. So why does this matter to gender biases? Well, imagine you're traversing this graph that you see on the right from the top to bottom, and you're trying to maximize on the score, which is represented by the color of the nodes. So green scores are good and red scores are bad. And the nodes here are going to represent the word choices that we just talked about. So if we ever enter a subtree that has no green scores, we know we can't go back up the subtree. So if we enter a subtree with no green scores, then we're never going to reach a green score, which leads to local minimum convergence. Now, if we say that the score is actually gender bias score, like a metric of how much gender bias a sentence has, then what we could say is that if you ever create a biased sentence and the context is so like highly attentioned that you can't leave that bias, it's essentially as if you're in local minimum convergence. So really the problem becomes an optimization problem where we have to create a sequence of tokens from the start token to the end token that optimizes on the bias score by choosing the least bias. So we want to create an algorithm that can find the path from the start token to end token with minimum bias. So what is that solution? Well, in our research, it is K-explorers Neural Network Traversal, or KeNNT. I'm going to call it KeNNT. So a KeNNT is a traversal algorithm that prevents gender bias convergence in the graph. Instead of just one explorer that was like that straight line going from the start to the end, KeNNT focuses on multiple explorers. Instead of creating one possible sentence, we don't take a risk and we create other possible sentences. So that creates like this lightning shape because at a certain distinct points, at certain distinct nodes, the model can branch out into different sentences. So there are multiple sentences being created, but there's still only one transformer. And so while this may seem efficient, like an exponential runtime, this is where Dijkstra's algorithm comes in. Instead of pursuing every explorer from the left to the right completely, we're going to selectively pursue one explorer at one time and at one token at a time. So we're going to select the explorer using a greedy algorithm, where we're going to use the least biased explorer and we're going to push it down by just like giving it one more token. Right? So you're repeating that process until one of the explorers reaches its end of token. So the model we use is a transformer model, a GPT-2 model fine-tuned on the WinoBias dataset. We know that WinoBias is made to have bias, gender bias, right? So the transformer will have bias in its understanding. So KeNNT's goal is to steer the model away from generating that bias. It's not changing the dataset though. So that being said, KeNNT is not a modified version of the transformer. It's not an AI algorithm, essentially. Really, it's an attachment that is running at inference time to help guide the transformer and like help steer the transformer away from creating gender bias. Right? And this allows us for multi-objective optimization, where we're optimizing on two objectives. One is gender bias, where we're trying to optimize and reduce the gender bias score. And the second is just contextual accuracy, which is what the transformer has learned itself. So based on this overview, here are the main components. I don't want to go too in deep into this because of time, but the general idea is first, we need to, at any given time, we have a bunch of possible explorers, and we need to choose which explorer should we pursue at one given time. So what we're going to do is we're going to choose the explorer with the least bias, and we do that by using a min heap or a priority queue, which is often used in Dijkstra's algorithm. Now, I kept mentioning a bias score, right? So what is the bias score? Well, this bias score is a commonly used bias score in some other gender bias research. It's a measure of gender polarity in a sentence. So how polared is the sentence toward male or female? So really, it's like, how much did the model want to choose, for example, how much did the model want to choose the word he when connecting to the word mechanic versus the word she, right? And so then at certain points, like I mentioned, the model is going to branch out into K paths, right? K from K-explorers means the amount of paths it branches out into. And so that point of determination is called the expansion point. When did we expand? And so we do that by using co-reference resolution. We just figure out whenever there's a new pronoun that has not been linked to a noun in the sentence before. Then when we want to do the expansion and split into K paths, we just take the top K words, the top K tokens from the softmax probability, right? Generally, we're only taking one. We're taking the best word from the softmax probability. Now we're taking the top K. And then traversing, you're just putting the sentence into the transformer's encoder layer, generating one more token. So from this, right, let's talk about the results that we got. Again, we are testing to what extent KeNNT can guide the model away from displaying the biases in WinoBias. WinoBias is the benchmark data set, which has a lot of bias on purpose. So we're going to give the models with and without KeNNT. The without KeNNT is our control model. And we're going to give both of these models prompts from WinoBias and compare them. So the prompts were just prefixes of some of the sentences in WinoBias. So some of the prompts were like the teacher was, the farmer was, which are just prefixes of full sentences that were in the data set. And using this procedure, we calculated the accuracy of KeNNT, which the accuracy is how much did the bias score at the end decrease from the model without KeNNT to the model with KeNNT. And remember, KeNNT is the one that's trying to decrease the bias score. So we found that on the K=4 model, we had a 95.93% accuracy, which we found was very promising, especially for feasibility. And so now with great accuracy comes the concern of runtime. So runtime is a concern, but our results showed somewhat promising runtime. Even though the absolute runtime for KeNNT is definitely higher than the model without KeNNT, the runtime is still linear. And this suggests that it's a feasible and practical technique, especially since the runtime is not harmed by like the procedures of KeNNT that I was talking, like the expansion, the exploration choice. It's not harmed mostly by that. It's harmed mostly by the co-reference resolution. And so we can, if we optimize co-reference resolution integration in our code, we can decrease the runtime by a lot. And that's documented more in my paper. And then we calculated the relationship between K, the value of K, and the runtime. The K is like how many paths get branched out into. That was also linear, which suggests that KeNNT is pretty feasible. However, then we analyze the amount of explorers created, and explorers basically represents the amount of memory we're using, right? And so at higher values of K, we saw that there was an exponential relationship between the amount of explorers and no, sorry, there was an exponential relationship between the length of the text and the amount of explorers created. And this is kind of interesting because the memory is exponential, but the runtime is linear. And so we realized that this represents how effective our implementation of Dijkstra's algorithm was, because Dijkstra's algorithm says that we do not need to check and process every explorer. We just need to process a specific one. So we essentially have an exponential amount of explorers, but we're only processing a linear amount. Now, memory is still an issue. So we have a proposed optimization when there are explorers that haven't been used that much, right? They're like inactive for a little bit of a couple iterations. We can just prune those explorers because they're probably not going to be active again later. And then now let's just look at some sample text that were created with KeNNT versus without KeNNT. I'm closing in. So in the first sample we have, you can read it yourself, but bias score was decreased by 100%. Then in the second trial, there was actually a near 0% accuracy. It was barely able to decrease the score. And this shows KeNNT's limitations because it couldn't escape the local minimum convergence issue. And then finally, in this third trial, while the accuracy was basically 100%, the meaning of the sentence changed, which we believed happened because the prompt was too short. So to conclude, KeNNT is an impressive and a feasible method of reducing gender biases in LLMs with a 96% accuracy on the K equals 4 model and a runtime that was linear. Now, this was a simpler simulation of gender biases. It wasn't like a large-scale ChatGPT simulation, but its impressiveness here shows potential for applications in a larger LLMs like ChatGPT. And it also suggests that KeNNT may be a possible method for solving other local minimum convergence issues and other optimization problems, like just to name a few, like gradient descent or something like that. And both of these things can happen through optimizations in the runtime and memory and the ways that we have documented. It's on the slide right here. But that's it. Thank you. If you have any questions, opportunities, or collaboration, here's my email and my number. But I'll take any questions.